Yeah,
Thank you,
great.
everyone, so much for joining another Balerion Space Ventures podcast. It's May 29th, and today I'm joined by Rahul Shirke.
Yes,
Am I saying that? How would I pronounce it?
it's Shirke.
Shirke,
Yeah,
the founder and CEO of Arceon, a company making advanced composites and materials for extreme environments. Rahul, I'm super excited you could be here. Thank you so much for joining.
yeah, likewise, likewise. My pleasure. Yeah, I'm excited.
So,
Yeah, sure. Yeah, go ahead. Sorry.
maybe we can kick things off and you can give us the overview of what you guys are building and the service you're providing and why it's so important right now.
Yeah, sure. So what we are doing, as you rightly mentioned, we are working on advanced composites for extreme environment, and we are targeting the family of ceramic matrix composites. Where we differentiate is that we have a process which is fast and economical and does not use any sort of coating on the fibers or exotic raw materials. So we remove all that jargon, and that's ours. Let's say that's our specialty and that's our core, and obviously how we design the pod. Right now, we are active in space and defense sector. So with space, we are active with nozzle extensions, then satellite thrust chambers and heat shields. So these are the components where we are deploying them with ESA under ESA project, but with an end customer. And on the defense side of things, we are active on solid rocket motor nozzles. We are scaling up the production at this moment as I'm saying this. And we are working on components like jet vanes, leading edges, and hypersonic aeroshells. So these are the components we're working with, again, with customers. So we work with OEMs or prime contractors. So that's where I think our market is, and we do not directly deal with the Ministry of Defense as such. But on the component level, we are scaling up production for SRM nozzles, for Rato boosters to your cruise missiles, and to your bigger ballistic missiles as well. So that's part of rocket nozzles. But on there are other components which are also getting scaled up, like leading edges.
And can you tell us about what led to the founding of the company? Maybe a little background on
Yeah,
yourself and
sure.
to the point where you saw that this is such a great opportunity and you have the right
Yeah.
solution that you started
Yeah.
this.
Yeah, so I've worked with CMCs in the past when I was actually studying and a bit after that. So, especially with the process, what we use melt infiltration process. And what I saw was the process can easily scale up, but it's still considered exotic and it was still longer for commercializing anything. I mean, one of the good examples of this baseline process is are the disc brakes from Porsche. So you can see the scale, how the process can be scaled up. Obviously, we do not use that exact same process, but that's where we thought we can enter different applications. We can make the application scope broader and commercialize it on a mass production and different application base rather than sticking with either automotive brakes or exotic domain like nuclear.
Got it. And for people who don't know this environment or what these materials go through, how brutal is this environment really?
Oh, it's nasty. I mean, with solid rocket motors, you have propellants which are uh, not just firing like high temperature, but there are like intense pressure, pressure of 100, 300 bar. Sorry for the US users. I'm going to use SI units.
No
So,
worries.
so 100, 300 bars of pressure, plus you have these particles of metal just attacking your nozzle, so it ablates like really fast. So you need a material which not only can withstand these conditions, but we are kind of taking a step forward than what the current knowledge or the current industry standard is. So that's our real mode, that we are replacing a multi-material system into one material. It's like one material every high temperature component.
And for this very fast, environment of hypersonics, orbital
Yeah.
reentry. It's kind of been happening for a few decades, but there's always been a lot of challenges. What were they doing back in the day that was right, that allowed them to have Apollo missions and rocket propelled jets um, to withstand these environments? And, how has that shifted to what we have today and what you guys are providing?
So back in the days, obviously, the rockets still fly, right? So there are systems in place, but they are complex, and that's why you also see the failures happening. And what technology or advancement in materials have done is that simplification of the system. So you have simpler systems, you have materials like what we do, where you can replace a metal structure of the heat shield itself because it can take the loads, it can take the mechanical and the thermal both. So that's where you simplify the systems, you advance your system. So in the past, obviously, there are materials, so you can use multiple materials, right? But again, it comes at a cost of something. So you're compromising either your performance or you're compromising some other factor which is going to be there. And material tech advancement in that has just made things simpler.
And describe in detail what these materials look like today. What would we see? And from, beginning when you have just forged metal or composite material to a
Yeah.
finished product, what does it have to go through?
So in our case, what we do is in the first step, we manufacture it just like a normal composite, a polymer based composite. So you can just, we call it shaping, just to simplify things. It's called shaping. You shape the part in this step. In the second step, what we do is we pyrolyze the material. That means we bake it. We bake it at a really high temperature in a vacuum, not in a vacuum, but in an inner atmosphere. And what it does is it takes out all the volatiles from this polymer, and the polymer gets converted to carbon, and you end up with a porous carbon material. It sounds very simple, but in this step, the part shrinks as well. So you can have a fantastic part in the first step, and it can get completely destroyed in the second step. We have seen this happen again and again. So that's our know-how how to control this. Now, in this third step, what happens is that we infiltrate molten silicon inside the material, and the molten silicon gets sucked inside because of the porous nature of the carbon. It's like capillary action. You are just sucking something through a straw. So it just gets sucked inside and it chemically gets converted to silicon carbide in the material. So it's a deep tech process. And we start with polymer and we end up with ceramic inside the material. And then the component looks like something like this, like a solid rocket motor. This is a Rato nozzle.
Got it.
So
And the the parts of the rocket and the hypersonic, is the whole thing just built out of advanced materials that can withstand this, or are there specific parts, kind of like how we see on Starship, they have the heat tiles on the bottom, not the top?
yeah.
How does it work in just, all of these very fast moving vehicles where you're putting these composites?
Yeah, so for heat shield, you do need like an insulation layer in between to safeguard your electronics, or because your metal is conductive. So even though my material can withstand, or high temperature material can withstand the thermal load, if the metal is conductive, so the heat can get easily transferred to your internal systems. So in case of like space systems, that's where you need that insulation, but defense systems you don't need these, because defense systems, they are operational for seconds, not for minutes.
And for people maybe not as technical, can you break down what fundamentally is different about Archeon's technology?
Yeah, so fundamental difference is, first is a design phase, like how we manufacture is keeping in mind how to scale the product. That means we target like how can we manufacture hundreds of these. So that's one part. Second is the process that we have our proprietary polymer. We do not use, as I said, any exotic material. We can ship the material if needed to the US, to the UK. Um, so that's not an issue at all. Third is how the process is placed. It's fast and economical. So being fast, you can also like just ramp up the furnace and it will be fast. But that's not what we do. We have tailored the cycle such that it's efficient. It gives us what we need in the end, and it still maintains the pace which we can where we can meet the orders of the industry. So there are processes which compete with us and they take months. We take like a week to produce. That's the difference. So that's our differentiator straight away there.
And what you're building today, tell us about the milestones you've hit and what you've been able to create from the moment the company was founded up until today.
So we started with aviation, to be honest, and then after COVID we pivoted to space. Um, well, obvious reason, aviation went downhill after COVID. So we moved to space and we started with these nozzles for satellite thrusters. So that's how it started. And currently, space projects are ongoing. There are field tests happening as I speak. So we have partners with whom we are testing. On the defense side, is moving a bit faster. So on defense side, we have we are entering qualification stage. We are entering production at scale for European companies. So next year we will start churning around 100 200 parts per month.
And you're based in the Netherlands.
Yes.
Um, what have you seen change in the European space and defense ecosystem since, you know, around the COVID times up until now? Um, has it become easier? Has there been any major shifts that have completely changed things?
Yes, major shift on both the sides. I can address the space one first. So, European Space Agency now has programs which are really fast. That means from the moment you submit an application or a proposal till the project is granted, the time line is like 2 months to 3 months. That's fast for a government agency. Yeah, I mean, previously it was not like this, but that shift has really pushed everything. It's also like the fail fast approach which ESA is taking, which is awesome because companies like us get a chance. We love that time pressure. So these projects are like for a year or something, and we love that pressure, and we love to deliver within that pressure. So that's what is happening on the space side. Things are moving really fast. There are companies getting opportunities to prove their tech at a as a at a crazy fast pace. The defense change has happened more on being independent from other demographics. So being autonomous has become the push. So so that's where it's more about like how we can produce things locally has become the priority. um, and that apart from that, you have seen the shift of just ramping up production, right? So that's all over the world, but Europe particularly is trying to be more autonomous at this moment.
And what are some of the changes that led to this dramatic shift? Why do you
Yeah,
think now is such a good time for a company like yourself?
it's just geopolitical situation over the world, all over the world. The Ukraine situation also pushed Europe to become more independent. Um, because the reason is you can keep buying things, but the things which you're buying should also be delivered in time, right? If you need things today, it's not going to help if it comes like after a year or two. So, and that's the major shift. I mean, there are motors being sent from Europe to Ukraine, and Ukraine builds the warhead there, and these are like at crazy fast pace. So that's the clear difference, that you need them today and you need them now. So So that's what has motivated Europe to push this change.
And what are you really building for? Like, what are some of the most important things? Is it reusability? Is it manufacturability to scale? Is it price? Like, what's some of the key drivers to the company and what customers are looking for?
For defense at scale, production at scale, there is absolutely, I don't think any other process can match the pace at which we can produce. So for defense, it is that. For space, for nozzle extensions, it's the weight reduction which happens, and the simplification of the system. No cooling needed, and the weight what we reduce with the nozzle extension for these companies, they can potentially earn millions with their payload. So that's a clear win for them. And with heat shield, it's about reusability. So you're going for lunar, you're going for Mars, and that's where these kind of materials become useful, because at some point you can't just keep using thick tiles. You need to also look into the weight aspect. You also need to look into like how you can fit more payload. So that's where it's about reusability as well for the for the heat shield part of things.
And I want to get a picture in my mind, just, how powerful this material is. If you could paint a clear picture of a side-by-side comparison of your composite materials versus, say, metal that you'd find on a commercial aircraft, and you put it through, you know, a ring of tests, like what could the composites do? And if you tried it with the airplane metal, what would happen to that?
So, if we are comparing Inconel, which is also commonly used in the space domain, they cannot withstand temperatures about 1,000 degrees Celsius. So, you need cooling. At any moment, you need to cool these materials. You can 3D print these materials, but at the end of the day, it's the material property that it just cannot withstand those high temperatures. So that's the clear differentiator between metal and our material, that the temperature capability is higher. The second part is the weight. It's Inconel is almost 8 times more heavier than our material. So that's again one of the factors, especially for the space domain, which is quite important. And then it comes to also lead time. So at this moment, the superalloys and refractory metals, at least in Europe, are difficult to source. So there are long lead times, and that's where we can cut down that lead time for the customer as well. So these are the aspects for if you compare with the metal, like superalloys with our material.
Got it. And I'm thinking about what this material would be like. Is there anything that, a regular person might find in their everyday life that, you know, kind of compares to what you're creating so they could say, okay, it's like a very special version of this, cooking pan or these tiles on the floor. What's something similar that is used that a lot of people would understand who aren't in the industry of what this product is really like?
Let's say you can say it like a damage tolerant ceramic. So um, on your screen, you again, uh, yeah, you can see the hole which is there, right?
Yes.
Yeah. If you try to put a nail through a ceramic plate, it will shatter.
Okay. Yeah.
If you see a localized damage, so you
And
can say a damage tolerant ceramic.
I got it. So it's like a tile, and if you hit a nail on it, it wouldn't shatter, it would go through.
No. And that's one of the reasons why you can make these structural components, why you can make a nozzle extension which is like 1.2 meter long.
What does it take to build these? Like the process of what materials do you start with, and how do you? end up at the finished product? Like what's happening?
So we start with carbon fiber, and we have our proprietary resin, like a polymer, and that's where we shape the part or make the part. Now the nozzle, what I showed you before, those had like chopped fibers. So we have different variants of the material. So we play with the fiber, we play with the type of fiber, we play with the volume of the fiber which is there inside. And it all depends on the application. It all depends on what structural and mechanical load are there on the component. Let's say for defense, for a solid rocket motor, we noticed that using a continuous fabric of composite over qualifies your component. So we are like, okay, we need to get to like something like chopped fibers. And there we change the length of the fiber depending on what pressure the component has to face. So that's the first step. Second, so we mix that together, make like a plate. Let's say, like in this case, I'll just consider plate. Make like a laminate plate, and then in the next step, what we do is we just place them in a furnace with nitrogen, and the temperature shoots about 1,000 degrees Celsius, and that's where everything gets transformed to carbon-carbon matrix with micro cracks in it. Okay. Now, in the last step, we place silicon granulates around the pod in a way that it should be infiltrated uniformly. That's very important. And it should be infiltrated in a way that it should not convert my carbon fiber. That's extremely important if you want the damage tolerance. So, these micro cracks, what we get in the second step, those provide like your guiding path for that silicon. So that silicon flows inside the material, converts this carbon into silicon carbide between the fibers, and the fibers are still intact there. So the fibers give the damage tolerance, and the silicon carbide gives the high temperatures stability. And that's how we end up getting this beautiful material, which has no coating, but it has inside silicon carbide, and that's what makes it special.
And to up until this date, like have has this been used in practice on a hypersonic or a return vehicle? Maybe you can walk us through some of the missions or tests that it's been on and maybe share a little bit about what it went through and the results you got.
Sure. So our material, we have done static fire tests on the nozzles itself for the defense application, and that's where I say that we are entering the qualification stage, right? And qualification stage in defense is just qualifying the subsystem itself, and that's after that you enter the commercial production. So we have done the static fire test for the material. We have tested the material with AFRL as well for satellite propulsion, and there was no structural damage. So that was again another successful test. Um, what um, what we did. Then on the nozzle extension sides, the tests are planned for this year, so they will be performed. Yeah, by the end of this year, if I'm not wrong. That's where we will validate the nozzle extension part. It's super interesting because this nozzle extension has a flange, and you can join that flange to a metal engine. So that's going to be interesting for the whole industry if that's successful. Because I remember Firefly also got this contract to make CMC nozzle extensions, and that's when we feel that we have already cracked on how to make this longer nozzle extension. Apart from that, we have tested leading edges for hypersonics, where the leading edges were put behind a solid rocket motor, and the motor was straight fired onto the leading edge, and the part survived. There was a steel structure behind the leading edge, and that survived as well. So these are some of the tests which we have performed in the past, and obviously the projects are getting carried forward.
Uh, what's it been like to grow to the stage that you're at in Europe and the Netherlands, uh, what kind of traction did you have to work really hard for, whether it's raising capital or finding talent or scaling manufacturing? Walk us through some of the barriers and hurdles that you had to go through to get to the point where you're at today.
I think with respect to innovation, Netherlands has been a fantastic place, and especially for us, our global reach from here is also very good. I mean, we have customers in the US, we have customers in the UK, and we have customers in Europe. So that says a lot. What where we find it difficult is to fundraise, and at this moment, to be honest, a lot of the help what we are getting is also through Ministry of Defense. We are actually funded by Ministry of Defense, and we also got another grant for increasing the production. But increasing private money is has been the challenge because we are not doing the whole bit. We are not doing the as Will Edwards from Firehawk said that we are not doing the sexy thing. We are doing something which is not a doesn't paint like a fancy story. So we are doing something which does its job. So that's where there has been, especially in Europe, raising capital has been a challenge for us. Um, but we have done very good with our customer base, so that's what we are happy about.
And how much of your roadmap is driven by defense versus commercial space?
Sorry, I didn't get that question.
So how much of the demand do you have from customers? How much of that is, defense and government versus a commercial space or defense company wanting it for their own systems?
So you can say at the moment it's 50-50 split. The space projects are longer. That's the difference. The defense projects are they hit at a much faster pace. Space projects have, again, you need to plan according to the company when they're going to fly, when they're going to test the flight model. So, and it's a long cycle. So, like for the nozzle extension, we don't see it commercializing at least till 2028, um, because in the coming year we will be just doing testing on these components. So the cycles are longer, but it's split 50-50. The team does both the work together. The good part is we are not playing with different components as such. We are playing with the shape. So a nozzle extension is a cone, but the same cone goes to defense as well.
Got it. And can you paint us a picture of what the space and defense world might look like 10 years from now if the access to these advanced materials becomes much easier to get? Are we going to start seeing, more hypersonics? Are we going to start seeing faster missile production? And in that world, like what's happening that's really driving everything you think?
I think for the space side, it's also the ambition to have colony on the moon, so that's driving it as well. So again, if you have to take things, if you have to like fly things from one place to another, you need lighter systems, you need efficient systems. So that's where the push is coming from. And on the defense, I have no doubt hypersonics is going to be one of the key factors in the future. I mean, we can already see like the world going into panic mode when Russia fired the hypersonic missile, and then all the hypersonic programs just took off. And they're like, okay, every country needs it. So, and you cannot make a hypersonic system without these materials. That's just given. You just cannot, just because of the pace at which the glide vehicles, hypersonic glide vehicles travel. You just need aeroshells based on these materials.
Yeah. And I'm thinking of the hypersonics um, as that industry grows, and we're in a bit of an arms race right now. Is that going to change warfare in general? Are we gonna see maybe small hypersonics that can fly at low range, or maybe swarms of hypersonics? I mean, I'm curious what the hypersonic future looks like. It is somewhat secretive, I know, but maybe you
Yeah,
have some input.
I can say so. We are like the connecting dot for different companies because they approach us because of the material. Uh, so at this moment, I can say that there is no such swarm thing being discussed internally, at least globally. Also, I can somewhere say that the swarm hypersonic part is not there. The most important part is getting a low cost hypersonic system in place. That's what is the first target, let's say, and that you can see also with companies in the US, right? So low cost hypersonic missile is the first thing, and then as the technology advances, I'm sure it's going to go with something like how can we make something like a hypersonic drone.
Yeah. And can these advanced composites be used for other applications, maybe like a shield against directed energy weapons or just high powered lasers, things like that?
Yeah, so high power laser is where we had got an interest in the past. Unfortunately, we didn't proceed any further research on that because laser is becoming one of the how does one of the threats for the modern warfare, right? Like so companies also want to know whether not only they can whether they can use this material, but also if this material is used in any other system, how can they penetrate this material? So so that's also an interesting aspect, but we have not gone into deeper research into that. Having said that, the material has applications other than space and defense as well. So in the industry like semiconductor industry, like ASML equipments, where which makes these chips. So the material has application inside that. The material has application in the industrial sector. So these are the other sectors where these are the cross sector applications. For Arceon in general, for the next 2 years at least, the focus is going to be space and defense, and eventually we will see how to tackle the cross sector roadmap.
And in the future, when this succeeds, what becomes possible that maybe isn't possible today?
So with respect to space and defense, you can expect travel like starships or colony on moon at a much faster pace. So that's one aspect. With defense, you can just have cutting edge tech, and that's happening right now as well. I mean, for a Rato booster, usually companies use graphite, and I just showed you a Rato booster nozzle. If you just change that nozzle, your range just increases. So you are basically just changing one component, and then that itself is making your system more efficient. So these are the changes which you will already see in the coming years, which are happening in the industry. Um, so yeah, so with the weapon system, it's just advancement of the system which is happening just right now.
You know, what kind of milestones should we keep our eye out for in the next, year or two that Archeon is really working at, and some things we might see in the near future?
So with the space domain, you will see that our extensions being tested, our heat shields being used in flight models, um, and with respect to defense sector, we are entering production as I clearly said. So that's something you will see next year, that CMC material being used in some of the systems which are currently which in the existing systems, I should say.
Yeah. And you can kind of look at this as a picks and shovel business. Um, so are large primes like coming up to you and relying on you to be, that strategic partner that helps? next generation aerospace defense vehicle weapon get across the line? And is that something that maybe that's the thing that's holding them up and they're waiting on getting that figured out? Or is there other things getting figured out and because you're in, they already have that box checked off. They don't have to worry about the heat and extreme environments because they have your advanced composites.
Um, No, so obviously they're looking at us not only one component supplier, they're looking at us as a company. As I mentioned, the goal is to become a company which deals with materials and makes components out of those materials for extreme environments. So these companies look at us from that point of view. So with the primes that we are working with, we are deploying one component. That's because you just can't do everything, but the roadmap says how to deploy the future components as well. So obviously these companies are looking at us as someone to find solution for their extreme environment problems. So we also have next gen material that we are already working with, where we will be having a ultra high temperature ceramic inside the material. And yes, there are companies which can make ultra high temperature CMCs, but our goal is how we can make it easy to scale up, and that's what we are doing. We are integrating that whole chain into our process, and that's our next gen material that we are working with. Targets, again, hypersonics as one of the application base.
Just thinking about material companies, historically, we've seen a lot of very hard and slow moving
Mhm.
companies, and that might not appeal to venture capital and investors. Why do you
Yep.
think the timing is finally right for a company like yours to become venture scale and backable?
So for us, we select the material. Some of these materials which are developed in the past are they're exceptional at lab scale, right? The bottleneck becomes production. The bottleneck becomes like industrialization. How are you going to produce the what the industry needs? And our philosophy has been that since the start that we are targeting scale, and that's the difference. So right from the start, the process what we use, even the new materials what we are developing, they are focused on how you can produce hundreds of these per month. So that's what makes, I think, Arceon attractive in that sense, because the focus itself is different. The focus is not making the most exceptional material with the most exceptional process, but how can we deploy this to the industry?
Yeah, I
And
get it there
sometimes,
fast.
yeah, also sometimes industry does not need the best material in the world. It needs what works right now.
So is your goal to build up a surplus and just have a lot of materials on hand for orders coming in, or are you still going to be producing and manufacturing each item for a specific order purchase?
So currently we because we were deploying demonstrators, it was project based. On the production level, it will be with the customers we decide to work with. So we will work on those components for them. Now for nozzles, for let's say a defense nozzle, the shape is more or less the same. So even if a new customer comes, it's not a big R&D cycle for us. We can directly start manufacturing at scale. So that's what the goal is. So right now, this next 6 months, Arceon's focus is standardizing multi-tooling. That means how can we standardize the processes and everything for making, let's say, 50 components together. So that's in the first step, and obviously processing like hundreds of them together. But our first step, how to make them multi-tooling together, and that's going to be the focus for now. And yeah, so that's the current goal.
And if a company were to try to copy you, where would they suffer the most? Like, what kind of challenges do you think they wouldn't be able to just figure out?
I say this to everyone, right? Like I can write the process down and I can give that to you. Our CTO and we combined have 40 plus years of experience with the process, and we still know how difficult it is to produce one component. It might appear to everyone else as a simple cone, but that cone takes blood, sweat, and tears to be produced. And that's exactly what I say. It's not very easy to replicate. Also, we start with a polymer, we end up with ceramics. So if you want to reverse engineer, sure, you won't know what polymer I used to start with. So
Yeah.
that's difficult to reverse engineer for sure. But the process itself is so deep tech. As I told you, there is shrinkage happening. There are micro cracks. One thing goes wrong, your parts are going to go. They're going to get messed up.
Yeah. Has there ever been like a specific test where, how you tested it, the data came back and you thought like, okay, we really have something that no one else has, and this is quite incredible. Can you tell us that story?
Yeah, I mean, the nozzle extension itself for what how we made that. So we had like let's say a strike of like failures with the part failing again and again, and then suddenly we had this one way of making this nozzle extension where we cracked it, which can be reproduced again and again, and that's what we were like. That's amazing because now we can do extensions of smaller, we can do nozzle extensions for a bigger nozzle, and that was just amazing. To be honest, every part which comes out has that excitement for us, uh, where we have successfully made it reproducible, and that's where when the whole team enjoys.
Yeah. What do those tests look like? Like, what are you doing exactly to them?
So for from our side, we do quality control checks, right, on these components. So we do CT scans to see whether there is any delamination or a crack going through the component, whether the silicon carbide is uniformly there in the material, or it's like ideally it shouldn't be in any patch sort of a place. So after these scans and after studying, as I said, this joining the flange is just the next level thing. What we have done, what our team has done. Yeah, unfortunately, I'm at home, so it's evening here, so I don't have the component to show that. But that's an amazing thing to see. Uh, and that's a game changer for the industry, for the space, definitely for the space sector. You can see companies are trying to make that, and somewhere we are like we have it.
Yeah. And if I were to walk into the facility on just a regular day, like what kind of things would I see? What's happening there?
So you will see obviously production at a lab scale right now, and now we are focusing on producing at scale. But you will, yeah, you will see the energy is like just innovative, like the every day when we enter the workshop space, it's like, so it's like some part is getting demolded and the team is excited, hey, what's going to come up and how it's going to look like, and so the whole team gets invested in that, and that's the beauty of our team, that everyone is not there just for as a, they don't see that just as a job, but they are truly invested and passionate about it.
Yeah. And for people listening to this, if they were to walk away from this conversation that we're having, remembering one thing about materials and why they matter so much and why the timing is so important right now, what would you want to tell
I would like to tell, if you see in the past, every major big breakthrough has some link to any some advanced material. It can be steel at some point, bronze at some point. So and it's high time that the industry also adapts to new age materials which are there and which can give the reliability at scale. So and the adoption is happening. So for me, it's I'm a bit biased towards material tech because my background is also I'm an aerospace engineer, specialized in materials. So I'm a bit biased that the next big step is also dependent on the material. It can be any industry, right? You can take from semiconductor to your space to defense to nuclear. Everything is happening on the material scale. You can see companies like General Atomics working on silicon carbide composites for nuclear application. So you can see that every sector is moving towards advanced materials and how they can deploy and unleash the actual capability of their system.
I love that. Well, Raul, it's been fantastic chatting about this. It's very interesting, and I think what you guys are doing is going to be, it's already critical and very important, but the future we're going to see is going to be quite different thanks to being able to have such advanced materials and composites. So I want to thank you so much for taking the time to join us today. This has been fantastic.
Likewise, I enjoyed it. Thanks, Aidan. Thanks.
Great. Chat soon. Take care.
Yeah, take care. Bye bye.
Bye.